fighting bears and shit.
Okay. All right. So today we're gonna do chapter 5. Too excited. Way too excited.
I'm having a good day today.
Okay, we're going to talk about eigenvalues and eigenvectors. Vectors. Anyone knows what these actually are? No idea. Okay. What are they?
Well, eigenvalues is lambda in the equation determinant lambda I minus a. Lambda eigenvalues is the solution to the determinant. I mean, again, somewhere.
Okay. Well, what are they geometrically? What's the interpretation geometrically?
Something about eigenspaces?
Eigenvalues are a special set of scalars associated with linear systems. i.e.
Okay, so remember we're talking about linear transformations, right? And in the plane they can mean something. You multiply by a matrix, you change one vector into another vector, right? Now, if an eigenvector is one of those vectors that under a linear transformation, it doesn't really change its direction. It'll only be scaled, right? So, eigenvectors are vectors that are only scaled by a particular transformation. The scale factors are called eigenvalues.
Excuse me. Thank you.
Right, so example, under projection to the x-axis, let's say that's our transformation, right? Meaning I.e. let's say in R2, i.e. I can take my matrix A to be, what's the matrix that projects into the x-axis?
1, 0, 1, 0, 0.
Right, you kill the y-coordinate, right? So, i.e. blah, 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 the vector I is an eigenvector. Right? Because if you look in the plane, right, I is right along the x-axis, right? So if you kill the y-coordinate, what does it do? Nothing, right? So I would be an eigenvector where its eigenvalue is actually the scalar 1, right? So here's this linear transformation. With other vectors, it'll change them drastically, right? So if you're pointing here, you'll now be pointing in that direction, right? Your direction changed. However, this thing, it does nothing to the vector I. There are other things where it would scale the vector, right? Or it might even flip it in exactly the opposite direction. Whenever a linear transformation does that, the vectors which it does that to, they're called eigenvectors, and their scale factors are called eigenvalues. Another example, it's, let's say, differentiation as a linear transformation. On R. Then, for example, y equals e to the kx is an eigenvector. And k is its eigenvalue. Alright, so that's an example. So if I have y equals e to the kx, if I find the derivative, I perform this linear transformation, what happens? Ke to the kx, right? I literally just scaled the function. I didn't transform it into a totally new function, right? So those are just some examples. So if you're looking at geometrically, in terms of an image, this is the, for example, in computer graphics, these are the things in your picture that won't really change, right? So if you're like doing a rotation transformation, right? Like you're in a first-person shooter or something, and the guy's walking around the corner of a wall, to look around the corner. The actual corner of the wall, that doesn't change, but pretty much everything else in the room is kind of rotating. So all these vectors would change, but specifically the guy that's on the edge of the wall, all those vectors running along there, they are not going to change. You're literally just rotating like that, right? But everything else in the environment is changing, right? So that's kind of, so in graphics terms, that corner, the edge of the wall that you're going around is a bunch of eigenvectors running along that, right? So it's kind of the guys that they're not really changed by a linear transformation, they're just probably scaled, or they may even stay the same. Right? And those guys are called eigenvectors, and their scale factors are called eigenvalues. So let's kind of make this more general. Definition. A, B, an n by n matrix. Which may represent a linear operator. What did I actually define first? Eigenvector, right? A non-zero vector x is called an eigenvector of A if Ax is equal to lambda x. Where lambda is called the eigenvalue corresponding to x. So basically I have a matrix that I can think of as a linear transformation. If I apply it to a vector and the only thing that happens is that vector gets scaled, it's called an eigenvector. We make it non-zero because there's a trivial case where you just set lambda equals 0, and if x equals 0, it doesn't make a difference. So the non-trivial cases are the non-zero vectors. Okay. Now let's get to that equation that was mentioned earlier. Note that if your Ax is actually equal to lambda x, that's the same as that, there's no harm in that. I can move everything to one side, and I would have lambda I minus A times x equals 0. Now, for this to have non-zero solutions, what do we need?
For them not to be the same?
Come again?
For what to have non-zero? The subtraction of one.
This equation. Did I actually number that equation? I think I did. I call that equation 1. So for equation 1 to have non-zero, for this meaning equation 1, to have a non-zero solution, what do you need? This is a homogeneous solution, right? How can you guarantee that it will only have a zero solution?
Just single.
Determinant of what? You can use the determinant, yeah?
Lambda I minus A.
Right, this here is a coefficient matrix. Now as long as the determinant of that is non-zero, you will only have the trivial solution. Which means to get non-zero solutions, we need the determinant of this must be 0. You need that the determinant of lambda I minus A equals 0. And did I number that equation? Yes, I did. Call that equation 2. We're going to be referring to this. Okay. So now here's the kicker. these two equations are just going to help us to find eigenvalues and eigenvectors. So how did I phrase this? Hence, the non-zero solutions to 1 are the eigenvectors. A, the lambda solutions for 2 are the eigenvalues of A. We find eigenvalues first. And plug them into 1 to find the corresponding eigenvectors. So these two equations are two very important equations. You have to memorize them. Start here. Start here. You have to memorize these very important equations. And if you're asked about eigenvalues and eigenvectors, these are your two go-to equations. Those are going to be the guys that help you find. What else do I want to mention here? More definitions. 2 is called the characteristic equation of A. It turns out if you have a matrix here, it's always going to end up being a polynomial. It might also be referred to as the characteristic polynomial. Yes, you're going to have to remember how to solve polynomials here. Review that from algebra as soon as you can. Another slight definition. The solutions to 1 form the basis of the so-called Eigen Space, someone else mentioned. So the Eigen Space is just going to be the space spanned by the solution vectors to this equation. Okay, now finally an example. It's not much theory here, it's mostly definitions, but those two are very important to remember. Find the eigenvalues and eigenvectors of A equals minus 5 to 2. Now what I'm going to show you will work on any n by n matrix if its eigenvalues and eigenvectors exist. But in practice I'll usually ask for a 2 by 2 or maybe a 3 by 3. It won't go higher than that. Because once you know how to deal with those, I know you'll know how to deal with the other ones. There's no reason to go too crazy here. Yeah, so find the eigenvalues and the corresponding eigenvectors of this matrix. right? Which you can think of as a linear transformation from F2 to F2. A two-dimensional space to another two-dimensional vector space. So first we find the eigenvalues. So what did we solve for that? Use the determinant of lambda I minus A equals 0. Right? So now lambda I is just lambda times the identity matrix, which just means lambda 0, 0, lambda minus the matrix A, minus 5, 2, 2 minus 2. We're going to set that equal to 0. This means that the determinant of lambda plus 5 minus 2 minus 2 lambda plus 2 is equal to 0. And what's the determinant of that?
Lambda squared plus 7 lambda plus 14.
Right. Cross multiply this times this minus that times that. So you have lambda plus 5 times lambda plus 2. It'll be minus 4, right?
Yeah, it should be 4.
And then you'd expand this, so what you said, lambda squared plus 5, 7, lambda. 5 times 2 is 10.
Plus 6.
Yeah.
So that's a 6. I think you thought this was a
Yeah,
plus.
that's them.
Right, so this is a 6. Right? So you end up with this polynomial. This is a characteristic polynomial. So they usually refer to this as a characteristic equation, and this is called a characteristic polynomial. And it's a 2 by 2. The n is going to give you the degree of your polynomial. So if it was a 3 by 3, you'd get a lambda cubed. If it was a 4 by 4, you get a lambda to the 4th, etc. Now we solve this for lambda. How do we solve that?
Lambda minus plus 6. Lambda plus 1 equals 0.
So I mean I have lambda
Negative
equals
6.
minus 6,
Negative 1.
or lambda equals minus 1. And so that matrix has 2 eigenvalues. Now once that's how you find the eigenvalues. Just start with this equation. You can usually jump from this point to this point. Or you don't need to write this to this. You just take lambda minus the first coordinate, negative here, lambda minus the 4th coordinate. You get this polynomial, you solve that. These are the corresponding ones. So now for each lambda, find its eigenvector.
Can you just plug in the eigenvalues there just for each?
Yeah, for each one. So remember, to find the eigenvector, you don't use this equation, you use the other one, right? So for each of these, I'm going to plug this into the previous guy, into equation 1. So here, let's do for lambda 1 equals minus 6. So I want lambda I minus a times x equals 0, which means I'm going to plug in minus 6 into this guy. So I plug in minus 6 here, I get minus 1, minus 2, minus 2. Plug in minus 6 here, I get minus 4. So in other words, I have this system, minus 1, minus 2, minus 2, minus 4, 0, 0. Now we're going to solve that. How do we do that? This is going to be a 1, 2, 0. This is row 1 times minus 1. And this actually be 0, 0, 0, right? So this is 2 row 1 minus row 2. Right? This is just a double of that one. So what does that mean? So this is x1, that's x2. How do I solve that?
x1 is equal to 2x, negative 2x.
x1 is equal to minus 2x2.
And then x2 is a free variable.
x2 is a free variable because there's no leading 1 here, so it's just blocked. And so this is just minus 2t. And so the solutions would be x is equal to minus 2t, t, which I can look at as t minus 2, 1. Now this guy is called an eigenvector. Corresponding to lambda 1 equals minus 6. I'm going to repeat the same process now for minus 1. Right, so under this transformation, the vectors that are going to be scaled are vectors that are parallel to this guy. And how are they going to be scaled? They're going to be scaled by a minus 6. So I'm going to flip them in the opposite direction and lengthen them by 6. Or there could be some other vector that I'm going to scale by minus 1s, so they're just going to be flipped in the opposite direction and then not scaled. So let's do that. Lambda 2 equals minus 1. So I'm going to plug in minus 1 into what was here, which I think we're going to have 4. Minus 2. This was minus 2. This was what? It was lambda plus 2. Was it?
Yes.
Which means that's minus 1. Plus 1. So we have minus 2, 1, 0, row 2, minus 1, 0. This is row 2 times minus 1. And this is actually double that one. So just take row 1 plus 2, row 2. That'll actually give me zeros everywhere. So here my x2 is equal to t. Let's use another variable, r. My x1 would be 1/2 r, which means x equals r over 2 r, which I can write as 1/2 1, which it's okay to take any parallel vector here. 1, 2, just use another scalar to get some nice numbers. Because we'll usually want to do something else with these vectors, so get rid of the fractions if you can. There's no harm in it. So this guy here is the eigenvector corresponding to lambda 2. So the eigenvalues eigenvectors are, because lambda 1 equals minus 6, its corresponding eigenvector is going to be
-2, 1.
-2, 1. And there's lambda 2 equals minus 1, and its corresponding eigenvector is going to be 1, 2. So under this transformation, vectors parallel to these directions will not be changed dramatically. They'll only be scaled by those numbers. Questions so far?
You said you don't always have to change it from the fraction, right? You can keep the fraction?
You can keep the fraction if you want. I don't recommend it, but you can. That's pretty much what we need to know from 5.1. 5.2, we're going to look at some applications of these. So, I mean, it's all neat and good, but what is the point of being able to find these? Turns out there are a lot of applications. One nice one is called diagonalization. Which is what 5.2 is about. Let's first talk about similarity. The matrix B, n by n, is said to be That should be obvious, the relationship is symmetric. Okay. So this is what it's said to be similar. Two matrices are similar if they share this relationship. Definition. A is said to be diagonalizable if it is similar to a diagonal matrix. i.e. there exists P such that A is equal to what was it? P inverse. D is equal to P inverse A times P. P is said to diagonalize A. Okay. So I can be given a matrix where if I can find the matrix P such that when I do this operation, I end up with a diagonal matrix, I say A is diagonalizable, and this matrix diagonalizes A, right? So I can pretty much kind of take a relationship that goes from A to the set of diagonal matrices, and this is the function. Why would we want to be able to translate A to a diagonal matrix?
Easy to take determinant.
Easy to do a bunch of stuff. It's easy to take determinants, all sorts of things. Diagonal matrices are really nice. It's easy to take powers, easy to take determinants. They're very nice to do operations with. The question is how? How do we even know if this can be done? How do we even know how to find that matrix? I'm not going to keep you in suspense. Eigenvalues and eigenvectors. That's the answer. And I think, did I mention the theorem here? I did mention a theorem. So here's a theorem. The following are equivalent. For an n by n matrix A. A is diagonalizable. Right? Meaning I can find a matrix P that does this. B, A has n linearly independent eigenvectors. So if I do what I did in the previous example, and I have n eigenvectors for an n by n matrix, and they're all linearly independent, it turns out I'll always be able to diagonalize that matrix. That's a theorem. Some things to note. A and P inverse AP. They behave very similarly, that's why they're called similar matrix. They have the same rank, the same nullity. The same bunch of stuff. They have the same eigenvalues. They have the same Eigen Space dimension. It's a bunch of stuff. They have the same determinant. They have the same trace. They have the same characteristic polynomial. Obviously, they share the same eigenvalues and eigenvectors. They behave very similarly. That's why it's similar matrices. What else do I want to mention? They have? Oh, they're either both and are both invertible or non-invertible at the same time. So you can invert one, you can invert the other. If you can't invert one, you can't invert the other. I wrote down the explanation for when this can happen, but do I want to actually go through that? Should I just tell you guys the answer? Just tell you the answer. Don't tell you at all. Don't tell you anything. You don't want to know. I've already lost interest. That might take a while to write down. Wrote a whole proof. Let's get to the point. Suppose A has linearly independent eigenvectors right? It has n linearly independent eigenvectors with corresponding I don't even remember if your book explained why this is, but I'm just going to tell you. Then I can write A as P D P inverse, where P is actually equal to this matrix. I take its eigenvectors and I turn them into columns and put them in a matrix. So you literally take the eigenvectors, throw them in the columns of a matrix. D will actually be this matrix. The corresponding eigenvalues to each of these eigenvectors, I put those along the main diagonal. So lambda 1, lambda 2, all the way down to lambda n. Zeros everywhere else. Yeah, and that's the summary. I don't particularly like how the book deals with this, but places like Wikipedia would have a nice example of why this is. So you can look at that if you want. Wikipedia is surprisingly good with math topics. I know, it's amazing. Sometimes I read a math text and I'm like, what? Then go to Wikipedia. Oh, yeah. All right. Yeah. Secrets. Okay, so now, yeah, so you'll always be able to, if this is true, if A has n linearly independent eigenvectors, and you know the corresponding eigenvalues, you can literally diagonalize A by choosing these as your vectors, right? Your eigenvalues, actually you line them on the diagonal of a diagonal matrix, and you put the corresponding eigenvectors as the columns in another matrix, and then this relationship will actually end up being true. And of course you will note also that this means D is equal to P inverse AP. Right? So you can literally transform A into a diagonal matrix. Right? Okay. Let's actually do that with the same matrix we had before. Find a matrix P. And D. Find a matrix P that diagonalizes. So there's your example. This is the same matrix from before. We already found the eigenvalues and eigenvectors here. Lambda 1 was minus 6. With its corresponding eigenvector was what? 2, 1 or 1, 2?
Minus 2, 1.
Minus 2, 1.
1, 2.
And the second one, 2.
And lambda 2 was minus 1 with 1, 2. With the corresponding eigenvector equals 1, 2. Right, so you go through that whole thing, you solve those equations, you get those answers. And so we can take P equals, just put the eigenvector here, 2, 1. And then for a lambda 2, 1, 2. And our D will be, I put the corresponding eigenvector for this one, which is minus 6. Corresponding one for this one, which was minus 1. Put those on a diagonal. And then you'd actually have A is equal to P, D, P inverse, which you can check on your own if you like. i.e. take minus 5. Oh. Note, what would P inverse look like? It's 1 over the determinant, right? So 2 by 2. So what's the determinant here?
-4
Minus 5. And you switch these two, and then you change the sign of those two. So that's minus 2/5, 1/5, 1/5, 2/5. And you can actually check that the matrix minus 5, 2, 2, minus 2, it's actually equal to minus 2, 1, 1, 2, times the matrix minus 6, 0, 0, minus 1, times the matrix minus 2, 5th, 1/5, 1/5, 2/5. That'll actually be true. So you do is find the eigenvalues and eigenvectors. Which, by the way, in like a test or a final, this would actually is an order that they usually ask. So they'll be like, part A, find the eigenvalues and eigenvectors. And then they'll say, part B, find a matrix that diagonalizes A. And then part C, A and what? Yeah, they'll give you A to a ridiculous number, like A to the 10, A to the 15th power or something like that. Right. Okay, so one application here is taking powers. So note, if your A is actually equal to P d P inverse, then let's say I take A to the kth power. What would that mean? It means I take P d P inverse to the kth power. Well, what does that mean? No, it does not mean none. It means I multiply this by itself k times. Now what's going to happen here? The p's and the inner p's will actually cancel each other. P inverse times P gives you identity. You're going to have a P inverse times a P from before is going to cancel that. You'll have a P inverse at this one is going to cancel the P here. And so you just have K D's in the middle and the P's are on the outside. So this means that A raised to this power is just going to be P times D raised to that power times P inverse. And raising a diagonal matrix to a power is super easy. You literally just raise the numbers on the diagonal to that power. Example.
I didn't understand how we got P.
Oh, I put the eigenvectors in the columns, right? So this first column here was actually the first eigenvector.
Okay.
And then this second column here was the second eigenvector. And then I put the corresponding eigenvectors. So the first one, the eigenvector in the first column is going to be the lambda 1 that corresponded to this. And the eigenvector in the second column is going to be the lambda 2 corresponding to that. So 2 by 2 I can find its inverse, and then this relationship will hold. Right? Once that relationship holds, I can raise A to a power just by doing this operation. And raising this to a power is easy. Raising A to a power is hard. You're going to have to multiply k vectors together. So here, what did I actually ask for? Given A equals minus 5, 2, 2, minus 2, find A to the 20. So you could spend the final multiplying a 2 by 2 matrix 20 times. Or you can use this fact, that I know that this is equal to that. since I know that A is actually equal to minus 2, 1, 1, 2, minus 6, 0, 0, minus 1, minus 2 fifths, 1 fifth, 1 fifth, 2 fifths. This means A to the 20 is just going to be equal to minus 2, 1, 1, 2, times this guy to the 20. That. Here's going to be minus 2, 1, 1, 2 times 6 to the 20th power is 1. Times that. Is equal to, actually, as so you'll just multiply these three together, which you can multiply 2 at a time because matrix multiplication is associative, and you'll end up with 4 times 6 to the 20 plus 1 over 5. 2 minus 2 times 6 to the 20 over 5. 2 minus 2 times 6 to the 20 over 5. 6 to the 20 plus 4 over 5. These numbers are going to be huge. But you can leave it in the 20th power.
So that can be considered as an answer when you're on the test.
Yeah. Yeah, because I'll ask you to do a power where doing it by hand is going to be like impossible. So the numbers aren't going to be very small. That's nice. Here's another application. Let's actually bring this to 5.4, differential equations. Has anyone taken differential equations yet?
Does taking it right now count?
I guess, yeah.
Okay.
Okay. Well, if you haven't, you should. Whether you're math or computer science, like differential equations have applications all over the place, including in computer science and computer engineering. A lot of stuff can be modeled by differential equations, all sorts of computer systems and circuits and all sorts of stuff. Okay, so they're super useful. I'm not going to go into everything. Essentially, these are equations involving a function and its derivatives. So here's an example of a differential equation. It's an equation, I have a function in it, and I have the first derivative of this function. A is a constant, right? To solve this, you need to find the function y that makes the equation true. Did I actually number this? I think so. Call this equation 3. So I need to find a function y that makes the equation 3 true. Now, you've actually seen a differential equation like that before. Back in Calc 2, when you were doing exponential growth and decay, turns out that was actually modeled by an equation like this. You can generalize it more, but it won't apply to linear algebra if you do. Right? Like I could have a plus another constant out here, but it wouldn't be applicable to linear algebra anymore, because you need to pass through the origin. So I need that y equals 0 must also be a solution. And in this case, y equals 0 is a solution. Okay, those who have done differential equations, what's the solution to this system, to this equation?
ax
Y equals?
E on T. You use E on T.
No, the
if it's function of x, it's equal to ax.
Yeah, that would be the constant.
general solution times a constant, right? Is a general solution. Right? So it turns out the exponential function is a general solution to that equation. In differential equations, you prove that all solutions can be written of that type and all blah, blah, blah. Okay, so that's a general solution to that differential equation, right? In many cases, we will need to solve a system of such equations. We did computer science, so consider, oh, there's also something called a particular solution. I could also probably mention that. Example. Given something like y prime equals 3y, and I tell you something like this. This guy here is called an initial condition. Right? It just tells you, I want you to find the function that does this, and at 0, its output is 5. Right, so then you know that y would be c e to the 3x. And since y of 0 is equal to 5, this means that when my x is 0, my y value will be 5, which means that c equals 5. And this means that y is equal to 5e to the 3x is a particular solution, as it's called. Right, so there's a general solution where you don't really know what the arbitrary constant is. It could be anything. Or there's a particular solution where there's a specific function that solves this equation and fulfills some condition that you impose on it. Now, we can make it a little bit more complicated. Given the system, something like this. I have n functions. y1 prime is equal to something like a11, y1, a12, y2, plus a1n, yn. y2 prime is equal to a21, y1, plus a22, y2, plus a2n, yn. So I can have an n by n system of such equations. These are all linear equations. They will pass through the origin of this n-dimensional vector space. Turns out we can solve all these all at once. Notice that this can be written as, I have a vector form of a derivative. There's a matrix times y where my y prime vector is just the list of derivatives. My y vector is just the list of solutions. And my A vector is the coefficient matrix of this system. And of course, no surprise here, being able to find the eigenvalues and eigenvectors of A will help us to solve this system. If A has n linearly independent eigenvectors and 1 to lambda n vectors with corresponding eigenvalues, lambda 1 to lambda n. And the solution to the above system is given by the following. Y will actually be equal to C1 lambda 1 vector times e to the lambda 1 t for x plus C2 lambda 2 e to the lambda 2 t. All the way up to C1, Cn lambda n e to the lambda n t. Example. Find the general solution to this system of equations. y1 prime is equal to minus 5y1 plus 2y2. y2 prime is equal to 2y1 minus 2y2. So I have two functions, y1 and y2, that obey this system of equations. For some reason that we won't cover. Note, this is the same as me saying there's a vector of derivatives is equal to this matrix times another vector of solutions. And since I already found these guys, this is minus 2, 1, number 2 is minus 1, number 2 vector is 1, 2. Those were what they were.
Yes.
This means that I can find the answer to this system by just doing C1 times the first eigenvector minus 2, 1, e to its corresponding eigenvalue minus 6x plus C2 1, 2 times e to the minus x. That's actually a solution. i.e., our first function will actually be minus 2c1 e to the minus 6x plus c2 e to the minus x. And my second function that will solve this system of differential equations will be c1 e to the minus 6x plus 2c2 e to the minus x. Now, unfortunately, in differential equations, they don't actually teach you that here. But if you do 392, you'll actually do this application. You'll actually cover this in that class. For those of you who are doing 392. Yeah.
The first term on the y, the general solution, is C1 times lambda 1 e to lambda x, or is it d? Because the rest of them are d. Why just the first term?
Oh, these are all x's.
X's, okay.
A lot of times in the differential equation, you think of your independent variable as time, so you kind of get used to writing these. Yeah, so that's it. So on Monday, we'll go over pretty much all the homework for chapters 8 and 5. And when we talk about the test, we have the test on Wednesday. And I might also talk more about the final on Monday, the final and the test on Monday. So you can stop there, go home, let that sink in, do the homework. And I'll see you guys next Monday. Always
It's not the job description. Be kind to the person. Raising their